All right, so why do we want to do dimension reduction? Here is an example. This is a very simple data set, US arrests. So here every observation represents one of the 50 United States. And there are 4 variables. Right? So murder, assault, and rape are the number of arrests under the corresponding sort of crime per 100,000 population, and urban pop is the percentage of population that live in cities. So like in Vermont, 32% live in cities, and in California, 91% of all population live in cities. So now we can, if we want to visualize this data set, so we could just pick 2 variables. So in this case, I picked murder and urban pop as my variables, and then I plotted every observation here as a point on the axis murder urban pop, right? So and then I constructed a scatter plot. But if I do this, then how do I know which 2 variables do I select, right? There is no way. Now what I could do, I could just do all possible scatter plots. So every variable versus every variable, right? But then if I have p variables, then the total number of plots that I'm going to do is p times p minus 1 over 2, right? So this is p choose 2. For 4 variables, this is okay. I will get just 6 different plots, and then I can stare at them and see some connections. Like I see that murder, these 3 plots, they display kind of not even these 3, so that there is a high correlation between murder and assault, between murder and rape, between assault and rape. So which probably means that if the state is criminal, then there will be a lot of crimes of every type. So something what I'm trying to say is that I can look at these plots and I can kind of figure out some information from these plots. But the problem is that with 4 variables, it is okay to do something like this, right? So it makes a lot of sense to stare at these scatter plots. But if instead I had, say, 100 variables, what would I do then, right? So with 100 variables, the total number of these scatter plots would be just too large for me to comprehend, right? So I wouldn't be able to. I mean, it would be just a complete mess. So it doesn't really make a lot of sense to stare at these pairwise scattered plots if p is large. So instead, I could do the following thing. So, and this is what dimension reduction is about. So I could try to find a map from my space, p-dimensional space, where my variables live, to the 2-dimensional plane, right? In a way so that whenever my x and i, xi and j are close to the original space, then their images are going to be close in the plane, right? So this is really the distance in RP, in the original space, and this is the distance in the plane. So what I really want is that if my observations are closed in the multidimensional space, I want the corresponding data points on the plane to be close in the plane, right? So I want to preserve distances somehow, if it is possible. And then I will just plot my data set as a single scatter plot. So it could probably look like this. So why do I want to do this? Because if I plot it on a single scatter plot, then there will be just one plot to look at, and then I could probably stare at it and think, all right, so are there any patterns here? So probably, I don't know, these observations are kind of similar, so maybe, and these observations are kind of similar. So why are they similar? So does it mean that these states are somehow maybe geographically close to each other, or maybe they are close to the border with Mexico or something like this, right? So I would try to derive any conclusions from here. Well, but then the convenience here is that there is just one plot that somehow tries to capture as much information as possible. So instead of looking at all possible scatter plots, I'm going to look at just one scatter plot that retains as much information as possible about the original dataset. So another scenario where we want to do this dimension reduction is if we have just too many features and we want to construct new features that somehow preserve the information contained in many original features. Like in natural language processing, so imagine that we have a lot of documents. So like, I don't know, Donald Trump's tweets. So we have a lot of tweets. So every tweet is a document. So we have document 1, document 2, document 3, document 4, and so on. And we have a lot of terms. So words, or sometimes terms are not just words, but maybe like numerals or punctuation. So maybe a full stop can be a token, right? So, and these are called terms. So there is term 1, term 2, term 3, term 4, and so on, right? So these terms could be like words. And then for every term and every document, we count how many times this term appears in this document. So like if term 1 is the word, say, I, we count how many times the word I appears in document 1. So it could be, say, 2 times. In document 2, it could be maybe 0 times. In document 3, it could be 1 time. Document 4 is 0 times, and so on, right? So term 2 could be the word the. And again, so it could appear 3 times, and 2 times, maybe 5 times, maybe 0 times, and so on. And so for every term and every document, we just count how many times the term appears in the document. And then basically rows of this matrix, so they become representation of our document. So every document is one observation, and the corresponding row, which just counts the number of times every word that we have in our dictionary appears appears in the document. So, and this is basically called bag of words. So in this model, we forget about the order of words in each document, right? So it means that our data matrix is just the raw this document term matrix, and the number of unique words in the vocabulary is going to be our P, right? So every unique word in the vocabulary gives us one feature. And this P, first, it can be very large. So, and second, this matrix, document term matrix, or the matrix X, which is the same thing in this case, is going to be very sparse. So most of its entries are going to be zeros. So we probably want to reduce the dimension, but not only because of that. So another thing is that words that have similar meaning will be represented as completely independent features. And words that are unrelated will also be represented by completely independent features, right? And we probably want to somehow create new features that somehow merge these similar words into just one feature. It makes sense, right? And this is another reason why we want to reduce dimension. So probably we want to introduce features that, features or new predictors or new variables, it's the same thing, that are more meaningful than the original variables. So, and such such considerations can be valid in a lot of types of data. So not just text data, but images, movies, whatever. So a lot of types of data that we have to work with in real world. So they are kind of have this feeling that when we really convert it to features, that there's going to be just a lot of features, and we want to reduce dimension to be able to construct better models and to be able to visualize the data. Okay, so this is the end of part 1 of the lecture. So now please do this little quiz.